Hi, everybody. I'm going to talk about chemical shift in NMR, how to use it, what it is, and how we find it in this video. So chemical shift in NMR, keep in mind it is your x-axis. So it is that horizontal axis at the bottom. It is going to be listed out in ppm, which definitely feels like a little bit of a weird unit, but we're just gonna roll with it. Okay. So if you're looking at a summary of NMR data, you might see something kind of like this. The chemical shift that we're talking about here is this first number. Okay, in our proton and NMR summary, the very first number. In the carbon, that's the only thing you're getting. Okay, carbon NMR is typically you're just getting the chemical shift as your only output in terms of your data. So that's what we want to be looking at here. These are all our chemical shifts. Okay, when we're looking at an actual NMR spectrum, this is kind of what we're looking at. So the 0 is always going to be on the right-hand side, and then your larger number is going to be on the left. For proton NMR, it's usually about 12. You might see them go up to 14. For a carbon, it's typically going to be 200 or 220. So if you just kind of think about that, we're talking about very, very different scales here and range. Okay, so a proton NMR, everything is really, really smushed down into one kind of small little area, 0 to 12 or 14. But in carbon's much, much wider range that we're looking at in terms of our chemical shifts that we're going to see. So keep that in mind when we're thinking about that idea of overlapping peaks. Much easier for peaks to overlap in a proton where you just have less space to put them all. In a carbon, there's going to be less chance of overlap because you're going to be able to see different kind of minor differentiations a lot easier. So when people are talking about NMR, they will use a couple of common terms here. So shielded and deshielded are pretty common. Shielded is going to refer to anything that's more towards the right, which is the smaller ppm side. Deshielded is talking about the larger ppm side to the left. Okay. Same goes with downfield and upfield. So they're typically used to say something along the lines of, this was shifted upfield, meant it going to a smaller ppm, or shifted downfield and went to a larger ppm. That's kind of what we're going to be thinking about here. So what is the shield? That's kind of the question here, and I think that's what causes a lot of people confusion. But if you kind of have a bit of an understanding there, it does make things a lot easier. So the shield is electron density, okay? So anything that removes electron density from either a carbon or a proton environment is going to be removing that shield, okay? So removing electron density leads to the environment becoming deshielded and then shifting downfield. Okay, vice versa is true, right? So if I have more electron density being added, it's going to get shielded and it's going to move upfield. So that's what that's what we want to think about. But at the end of the day, if we're thinking about more delta plus, kind of like more of that partial positive charge, we're going to be more deshielded, and it's going to be a larger ppm. Okay, so that's what we kind of want to think about. Electron density is our shield. Removing it is deshielded, going downfield. Adding onto it is becoming shielded and going upfield. Okay, so let's look at some reference tables. So these are the tables that you're going to be using for the class, the lab, and this will be available on exams as well. So I'm not expecting you guys to memorize these values. You will probably start memorizing them just from a lot of constant use, but I don't need you to be doing flashcards on these or anything like that. So if we look at some chemical shifts for the carbon NMR, make sure that we keep a note here and be really careful with this. This is only looking at the carbon atoms in the molecule. Okay, so it only shows you carbon atoms. You are never going to be seeing a peak arising from an oxygen or a hydrogen in a carbon NMR. Okay. Same with the proton. When we're talking about a proton NMR, we are only showing what's happening with the protons or the hydrogens of that molecule. Okay, the carbons and the hydrogens, and they are going to be separate pieces of data where you've got one spectrum for carbon and one spectrum for the proton. Um, that does allow us to see a lot of different things, and as you see as we kind of go through this, we're going to get a lot of really good data out of the two NMR spectra here, where we have all of those pieces of a puzzle that we can kind of put together and learn a lot about the actual structure of the molecule that we're working with. So when we're working on carbon chemical shifts, you can kind of see what I'm talking about with the electron shield here, where if I don't have any electronegative atoms nearby, so nothing kind of withdrawing electron density towards it, I'm at pretty small chemical shift, right? I'm at the 0 to 50 ppm. This is all of our alkyl type stuff. As soon as I start adding on an electronegative atom onto that carbon, so now I've got this inductive electron withdrawal kind of like pull away, that carbon is becoming de-shielded because that oxygen or nitrogen or electronegative atom is starting to pull electron density away from that carbon and make it de-shielded and pushing it downfield. Okay, we can see the same thing with aromatic rings or alkenes. That aromatic ring or the alkene is going to be kind of taking some of that electron density away from the carbon and putting it into other places, basically. It becomes really defined when we start looking at our carbonyls. So now that we've got a carbon that's double bonded to an oxygen, now we're seeing a really big shift downfield because that carbon is becoming very de-shielded. You can think about this through the lens of resonance, because since I have that resonance structure right there, that carbon is becoming de-shielded. Okay, if I look at my ester resonance, I can see something similar. Okay, where I do have the carbonyl oxygen pulling away, but if you look at this other oxygen here, I have another resonance structure where I can push electrons in towards that carbon. Okay, so this resonance structure is actually helping me to lessen the effect of that de-shielding a little bit because we've got something that's putting electron density in. So this is becoming slightly shielded. Okay, so if we look at the chemical shift between something like an aldehyde or a ketone and then an acid, amide, or ester, our acids, amides, and esters are shifted upfield compared to the aldehydes and ketones because of this slight shielding effect. Okay, so the resonance can help you out a lot here in just terms of thinking about that and where the electrons are going and what the shifts are, what kind of shielding or de-shielding is happening. You can see the same types of situations in the proton chemical shifts, except now obviously we are looking at the protons, so keep in mind they're all boxed here. So our just kind of plain Jane alkyl type protons are going to be pretty far upfield. They don't really have anything to take away that electron shield. They're all pretty covalent. Nothing really to do there. As we start putting in more kind of pi bonds, more electronegative atoms, we're going to see that shift start to happen towards the downfield side. Okay, where we have our allylic, benzylic, alpha to carbonyls. In a certain region, we've got our triple bonds, we've got the alpha to electronegative atoms. So again, having that H that's getting electron density pulled away by the electron negative atom there, your aromatic area, and then way up here you've got carboxylic acids, aldehydes. Okay, so they tend to be pretty obvious when you've got them because they're like way out in nowhere. If we're talking about specific functional groups in proton NMR, it is kind of helpful to note that when you're looking at a proton, that as you have more protons on the carbon the carbon of interest that you're working on, that chemical shift is going to be more shielded. As soon as you start adding more carbon groups on, it's going to start shifting it downfield a little bit because that carbon atom is a little bit more electronegative than the hydrogen. Okay, so as you get more carbons on an atom and fewer hydrogens, you're going to start to see a downfield shift. For amines and alcohols, they have kind of an annoyingly large range of chemical shift spots. And they're typically going to be showing up as broad singlets. Okay, and that's just because of the acid-base properties of that OH, where we can think about it popping on and off too much to be able to actually lock down a particular peak shape. So it's usually going to be a broad singlet that you're looking at. And so that's kind of what we're looking at for our chemical shifts. So that is the first little piece of the puzzle here. Alrighty, let me know if you have any questions and I will see you all later.